Hi. So now let's have a look at the set covering problem. So the set covering problem is still an integer programming problem, but now we are interested in generate covers, and a cover is simply you can think of a cover as a subset of elements. So suppose you have a collection of points like so, and you know that each potential location, say this, maybe this or this, they have a covering potential. So say like these points, they cover these like such. So the orange points, which are candidates to be placed, they have some sort of covering potential of the blue dots. And you can see as I was drawing that some of them overlap in terms of coverage. So the coverage, let's say that the coverage of this node involves these 3 points there, and the coverage of this node involves again the coverage of these 2 points. So there is some redundancy going on. And what you're trying to do is to make sure all points are covered, but you're trying to somehow minimize the number of servers you are locating, or centers. So the set covering problem is typically posed in this setting where you have centers that can be opened at any possible places, and these centers, they serve regions. So they could be, for example, hospitals, they can be schools, they can be police stations, fire stations, things like such, emergency response stations. So we call them services centers. And then if a center is open at that location of candidate location, then it serves a subset of other regions, and it has its opening cost, Cj. Okay. It might be so that this node J is the same. So sometimes we're talking about cities, and it might be so that actually you have the city both playing the role as a potential location and a place to be served. When if you locate a service station at that city, you assume that the city is served. And that's just one example. But let's look at this. So how we would model this. You can see that this clearly is this combinatorial optimization problem where we are trying to make a selection T where T is such, then when I look at all the covered elements by each element in T, what I obtain is the total set of nodes. So the union of all coverages returns me the list of all points I need to cover. So I have to have total coverage. Okay, right. So this is a better picture of what I've just shown you. This is just one example, and it looks like it's this idea where we have a country here. And what we can do is divide the country in these hexagonal cells. And each of these blue locations, they represent potential candidates, potential places where I can locate a facility. And it goes like so that whenever I locate a facility at a given node, then I can serve all my immediate neighbors. So if I locate a facility in 3, then I serve 1, serve 2, and serve 8. Okay, so that means that S3, the coverage of 3 is 1, 2, and 8. Okay, like it is shown here. So if I do the same thing for S4, S4 is 2, 7, 6, and 5, or 2, 5, 6, and 7. And you can see the 2 is overlapping. And what you're trying to figure out is how many service centers you need to make sure you cover the whole country. Right? So how do we model that? I mean, I think that the main difference from what you'll be seeing up to now is this presence of this element, which might be somewhat confusing. So this sort of matrix actually is going to appear all the time when we talk about combinatorial optimizations and covering problems. And basically, to model the set covering problem as a binary integer program, we need this incidence matrix, which works exactly like the incidence vector we had before. But in this case, it is a parameter of our problem because we can figure out the incidence matrix just by looking at the structure. And the matrix looks like so. It's a matrix m by n where all entries are binary, and it tells us that if a service center is located at J, then it will serve I if this is 1 and 0 otherwise. If we go back to the example we just seen, so a matrix A that has rows I and columns J. So if I'm thinking of, say, J equals 3, right, it will be such that in positions 1 you'll have a 1, 2 it will have a 1, 3 will have a 0 all the way to the 7th position, and then the 8th position will be 1, and then zeros all the way. So that will be the column associated with J equals 3 in the matrix I. So that will be I1, I2, these two, and then I3, 0 all the way to I7, 0, and then I8 would be this one again, and then 0 everywhere else. So just to give you an example, and then once we have this matrix, we can basically have this variable xj telling us whether a center is located at location j or not. And we can, the way we look into coverage is we're gonna look at these elements of my matrix ij, and I'll multiply them my j's. And for when I sum this for all j's, what I have to observe at this is being greater than 1. Notice that this is an interesting sort of, it's something that can be thought about and can vary different problem setting. If you are willing to allow for overlapping, then we're talking about that it has to be at least greater than or equal to 1, because it might be so that your selection is such that even though it minimizes the cost, which by the way we can put in here as being minimized, the sum j in n of cjxj, this is the cost for locating the facilities. It might be so that you allow for overlapping. Otherwise, if overlapping is not allowed, you can think of this as being exactly equal to 1. But that might be, that might be troublesome, because in some cases it might be such that you cannot get this perfectly non-overlapping coverage. So it's problem dependent. And this is the final form as we see. So basically, this is the coverage constraint. Say when you look at the matrix, let me go back and look at this. So now, because you have this column for 3 and you will have a similar column for 4, 4 will be such that it has 0 here because it doesn't cover 1, but it does cover 2, 3, 4, 5, I don't know, you will have a 1 somewhere in the middle. This would be a 1 as well, and so on and so forth. So basically what you're trying to do is when you look at your selections at the row direction, so in this case for 2 could either be covered by S3 or S4. So you're looking at when you look at these directions and multiply by the x variables each of these elements, you're making sure that you have at least 1 covering the location. Yeah. And this is the set covering problem. Another super important problem in the realm of combinatorial optimization is the traveling salesman problem. So the traveling salesman problem is it's behind many practical applications in the realm of logistics and supply chain management. And there are many companies out there that heavily rely on a former traveling salesman problem, or a generalization of it called vehicle routing problem, to plan daily deliveries of goods, distribution of things among of retailing centers and things like that. And the idea behind the problem is actually a problem that is one of these problems that is very simple to explain but really hard to solve. And it goes like this. So you are a salesperson and you start at a given node, say 1, just to make things easy, but it could be any node really. And the game is that you have to leave 1 and visit the other cities, but in a way that you only visit each city once, and you visit all cities only once each, and you return to the initial point. And you do that minimizing the total distance traveled. So it might be so that doing something, if these are representative in terms of distance, it might be so that this is, say, less of a distance than doing something that looks like this, right? So this sequence of nodes being visited is called a tour. And one characteristic of a tour is that it can be presented as a permutation of, so if you have n nodes, it means that the number of tours is n factorial. Because you have, the first node, well, it's actually n minus 1 factorial because you're missing the first node there. But basically means that you don't have any questions about the first node because you are there, but then you have 5 options, then you have 4 options, then you have 3 options, then you have 2 options, and then you have to return where you were. So in this case, it would be 5 factorial possible tours. So you can see the search space of these things. They grow really, really fast, and very quickly you end up with problems that you can't really solve unless you're doing something specialized. So here is just a picture showing one example of what would be a solution for that. We go 1 to 6, 6 to 4, 4 to 3, 3 to 2, and 2 to 5, and 5 to 1. There is a lot of material online about the traveling salesman problem. There is definitely worth checking out. Nowadays, with these specialized methods, people can solve really large traveling salesman problems. And there is also quite a few interesting competitions associated with being able to solve specific instances. Right. So how do we model that using a integer program, integer program in this case? We're going to use, again, these vectors xij, and what they're going to telling us is basically whether I went from city I to city j. From city I to city j. So if city j is visited directly after city I. And I'll consider n cities. We just will assume that we don't cycle, so we don't have to worry about these. So xi doesn't exist. Okay. And then the problem becomes, it actually looks like a problem we've seen before. So we are minimizing the sum in I in n, sum j in n of cij xij, subject to, when I think about whenever I'm getting to a city from I must only, so this is all the cities to which I'm going from I can only go to a city and a city only, and that has to hold for all I in n. And likewise, whenever I'm arriving at a city, so I'm thinking of all the cities I'm coming from, I can only be coming from one city and one city only. And this are binary variables. And if you look at this and think about the first problem we've seen today, it is exactly the same formulation, right? This problem is identical to the assignment problem. Oh, by the way, I'm adding here, making explicit that you don't have xii and xij in the story. And likewise, I'm saying that when I'm generating my variables, they don't exist when I equals j. So that's the slight difference because you could have in the assignment problem I with 1 with 1, 1 with, or 2 with 2. And here we're not saying that this is the case, but you can see it's the assignment problem. But this is not the end of the story, because this formulation is not correct, because it allows for something that plays traveling salesman problems, which is the source of all evil. Why is it so hard to solve traveling salesman problems, which is the notion of subtours. So if you look at this formulation, you can see that it would allow a solution that looks like this. So these are my 6 nodes again. And if you look at node 1, 2, 3, and 4, 5, 6, I have this 1, 2, 3. Each node has only one entry and one leaving arc. And likewise here. But this is obviously not a tour, unless the traveling salesperson invented teletransportation and did 1, 2, 3, 1, I don't know, 1, 2, 3, teletransport to 6, 4, 5, teletransport to here, to 3 again. I don't think even with teletransportation you can actually solve this. So this formulation doesn't really prevent this. So that means that we need to add more. So we need more constraints that further prevent this. And that's where things get tricky, because these constraints, which are constraints that have the role of preventing these so-called subtours, they are often based on the notion of subset of your set of nodes. And that means that the number of constraints that you might have like so is something like a summation in J equals, I don't know, you need at least 3 to N of N J to J. So you have to think of all combinations you have of 3 nodes that can form a subtour, and then add to that all combinations of 4 nodes you can form a subtour, and then you have to think of all 5 nodes. So this, you can't form a subtour with only 2 nodes, so that's why I'm putting at least 3 here. And this is a really large number. It means that you have a really large of constraints that you have to take into account. I think in some cases this can be actually smaller, but no, the point stands. It means, I'm trying to say is that you might have a really large number of these constraints to take into account, which might make your model simply not efficient or even not solvable. So the first type of these constraints is this that is called cut set. So basically cut set is telling us the following. What we can do is, if you observe a subtour between, say, 1, 2, and 3, what you say now is that when you look at the arcs that have as origin S, so, you know, arcs leaving this node, arc leaving these nodes, and arcs leaving this node, and you sum among them, you have to have at least one connecting to a element N, to a node, that is not in the set S. So basically, what you're trying to say is that there must be at least one arc leaving the subset S. So it can be this, or it can be this, or it can be this. At least one. So that would break a initial subtour that you would have here. For example, that because in this case, you can see that this constraint is not satisfied because the J's are all in the subset S. So you want at least one arc leaving this node, leaving this node, leaving this node, being such that it leaves the subset S. So this is cut set. The other one is called subtour elimination. And you basically look at the number of arcs you have within a subset. And the trick now is to say, if you have the same picture we had before, and you think of those forming a subtool, you know, these potentially forming a subtool, what you say is that within the set subset S, the total number of arcs you can have is the number of nodes minus 1. So between these 3 nodes, you can only have at most 2 arcs. And if it was a subtool with 4 nodes, you can have at most 3 arcs. And then it has to be until n minus 1, because if you do that when this is the set is all nodes, you're eliminating the tool, and you don't want to do that. So this is the subtool elimination constraint. And the way to deal with these constraints is something that we won't explore much in our course, but it refers to the notion of lazy constraints. So this funny name for lazy constraints means that it allows you to, instead of having these constraints all at once considered, what you can do is to simply not have them considered, solve the problem, observe the occurrence of subtools, and if they do occur, you can include the constraint and re-optimize, and keep doing that until it's such that you observe a feasible solution. So this strategy is called the delayed constraint generation, or lazy constraints. And the main idea is to prevent you from having to, from the get-go, considering all of these constraints at once. This is the strategy, by the way, we're going to explore also when we talk about more sophisticated solution methods later in the course. But anyway, here is a very small example where then you have these 2 subtools we defined before, and then let's arbitrarily decide that I'm going to have a subtool elimination constraint for this. I can actually add one for this and one for this, the same run. I mean, what's the difference of adding 1 or 2 constraints? And so the formulation of the cut set constraint would be like this, saying that because it's 1, 2, 3, I need to have one arc going from 1 to 4, from 1 to 4, 5, from 1 to 4, 5, or 6, from 2 to 4, 4, 5, or 6, and from 3 to 4, 5, or 6. So that's the subtool elimination, leaving the subset. And this one is basically saying, if I think of the arcs 1, 2, 2, 3, 3, 1, and the reverse, of course, 1, 2, 2, 1, 2, 3, 3, 2, and 1, 3, 3, 1. This cannot be greater than 2 because I have 3 elements. And that's it. All right. So that's the traveling salesman problem. Really, really important problem, and really challenging computationally as well. The last, I think this is actually a good stopping point for us. So let's stop here, and in the next video we'll talk about the last 2 now mixed integer programs I wanted to show you in this lecture. So see you in the next video.